Our final speaker for this morning's session is Robbie McNaughton. He's the Principal for Solar Thermal at Fortescue Future Industries, and he's going to talk about their efforts in gigawatt scale projects for green hydrogen production and how solar is going to integrate with that program. Thanks, Robbie.
Okay, thanks. Hopefully everyone online can hear me.
Yes.
Excellent. That's a good start. So yeah, I joined FFI, Fortescue Future Industries, just over 6 months ago now. I think I've made one trip to Perth. Unfortunately, they won't let anyone in, but it's certainly been exciting times. And some of the visions that that Fortescue have around energy and around hydrogen are absolutely massive. And when I talk gigawatt scale, we're talking hundreds of gigawatts, and it's a great opportunity for solar, but for all types of renewables: wind, geothermal, hydro, the whole suite of technologies. Of course, now that I'm working for a listed company, it's important we remember that these are fairly general statements, and you really need to check out the ASX actual announcements for any particulars on projects, etc. For those who don't know, Fortescue's has been an iron ore miner for the past around 15 years. And one of the things that they're very focused on is actually owning their supply chain. So when they developed their iron ore assets, they actually developed the rail lines, the ports, the shipping, everything through to the customer. And when we start talking about energy, there's very much the intention to do similar types of things. They're very big on investing within the business in new areas, and advancing green energy is one of these areas. Decarbonising their operations is actually the genesis of what Fortescue is actually trying to do. But obviously that vision has grown quite significantly now. Approximately November 2020, a new subsidiary was developed called Fortescue Future Industries, and it's really starting to diversify Fortescue from a straight out iron ore miner into an energy business or an integrated energy business. And that Fortescue Future Industries business is really about taking a global role in renewable energy and green products as well. And you'll see Andrea Forrest, the chairman, doing a lot of talk. He was at COP26, and there was actually quite a contingent from Fortescue there, really starting to try and introduce the idea of green hydrogen into the language, as opposed to some of the other colour variations that everyone likes to talk about. It's interesting listening to Andrew speak. He often talks about the existing industries don't actually have to prove that green hydrogen is the wrong way to go. They just have to put enough doubt in your mind that all of these other options are possible. So I think their presence there and their continued discussions around green hydrogen are actually really important for the whole renewable space and driving that forward. So really the grand vision is to take renewable energy, generate green hydrogen, turn it into products, whether it be ammonia, some of the other energy carriers that I'm sure you guys are aware of, and also all the way through to actually embedding that renewable energy into our metals as well. So as I said, the real genesis of this was actually around decarbonising Fortescue's own operations. So that's where this all started. And so there's actually been quite a lot of work already completed in trying to decarbonise all the separate operations that go on when you mine iron ore. There's been success on the rail systems. The shipping engines have been converted to ammonia. These are still in the warehouses, but they are at the scales that we see in ships. We've commenced conversion of a ship. So we've actually bought a ship specifically to run on ammonia. so that we can start to understand some of the other challenges that might not be obvious when you come up with a vision this grand. In addition, we're seeing work going on as far as integrating hydrogen into some of the equipment that gets used within the mining systems, as well as the haul trucks where we have batteries getting integrated into that. So as part of that entire green energy chain, all of the different ways we might be able to integrate green energy into our mining operations are being tested and explored to try and, once again, tease out what works and what doesn't work and what's practical. There's also, I guess, a move away from traditional ways of making steel as well. So they've demonstrated in the labs high purity iron generation from iron ore, which is also a great success there. Project-wise, there's things going on all over the place. And this is a couple of weeks out of date, and there's projects that get announced every week all around Australia. I think there was a few in the Hunter Valley recently. There's projects down in Wollongong, southwestern Australia. There's also projects that have been announced as well. The Pilbara is our main focus for the moment. That's that decarbonisation of the iron ore operations. But certainly Queensland, where we're in Gladstone, where we're starting to talk about building factories for electrolysers, for instance, as well as redeveloping some of the port facilities there so we can actually start to export green energy out of it. And of course, Tasmania, which will probably be one of the first large-scale hydrogen electrolyser projects that actually produces hydrogen. And of course, worldwide. So our chairman, Andrew Forrest, has travelled the world extensively. I think I don't know what the final number is, or it's not a final number, but we're talking 130, 140 countries he's managed to visit in the last 2 years. And it's every corner of the world that you could ever imagine. From the solar point of view, I'm sure you've all got a map of where the solar resources are. All of those countries are being explored, and you know, negotiations are going on as far as what sort of land availability there is, what sort of access to infrastructure there may be, how much infrastructure we need to build on our own. The goal by 2030 is to be able to supply 15 million tonnes of green hydrogen. And I'll explore exactly how crazy that number is in a few slides' time, because it's quite massive. One of the other things that Fortescue is very big on is actually, I guess, representing themselves well in the communities as well. And so there's a number of, I guess, underlying principles that they're very strong on around education, around compulsory labour, forced labour type issues, modern slavery, of course, and zero forced marriages. And I think it was already mentioned in the talk previously that supply chain's going to be really critical for this transition. And enforcing some of these principles is actually going to be really interesting when we start talking about supply chain as well, because a lot of those really cheap supply chains are reliant on some of these types of issues. So this is where things get a little tricky, and this is where the engineers come in and scratch their heads quite a lot. So we have a grand goal of 15 million tonnes of hydrogen annually by 2030, which is awfully close. We've got renewables as our main source. They're inherently intermittent. So especially solar, especially wind, even hydro, we get seasonal, we get droughts. There's a whole stack of variations that go on there. There's actually the electrical system. So a lot of the locations we're actually looking at, we will be larger than the national networks. So we're actually got to build our own transmission, have private power lines, the whole works. And so once you sort of combine all of these challenges together, we also need to be flexible in how we actually run our electrolysers and the conversion plants that actually turn that into a fuel that can be used anywhere in the world. So some quick mathematics, 50 million tonnes, just over almost 2 million kilos an hour of hydrogen production, a huge amount of energy every year. If we had a continuous process of generation, we'd need somewhere around 85 gigawatts. When we introduce capacity factors and availability of these renewable resources, our installed capacity is going to be upwards of 200. I suspect it actually might be even more than that, to be honest. So there's some real challenges there. And when we talk supply chain, this is actually the world's production, again, on top of what's already going on. And so that's why you are starting to see FFI make some investments in technology companies to try and, once again, bring some of those potential limitations into its own control so that they actually are able to try and influence what's going on in that supply chain as well. Intermittency introduces some challenges, and that top point there around solar, reliable during sunlight hours, assuming we're in a good spot, like the Pilbara, always off at night. And I've put that there because it's amazing how many oil, gas and mining engineers don't understand that. It's been one of the real challenges that I've had to I guess, take on and try and educate within the business. Even now, there's a massive discussion going on exactly what capacity factor means and what you can do with it. You can't add it, apparently. So you can't put 3 solar plants next to each other and come up with a capacity factor of 1. And it seems obvious, but from people that are so used to being able to create something that brings a resource out of the ground, for instance, at a constant rate, and all of the design processes that go on past that point are all based on a continuous flow. With solar especially, but also wind, we have to come up with innovative ways that we can actually buffer that intermittency so that down the line, the ships can come in at a constant rate and take product away. And we're still very much learning where the best spot to put those buffers is. There are some ways around it. Diversity of technology helps. So if you've got solar and wind, that de-risks your supply quite a lot. Obviously, with forecasting, you can actually start to learn to turn down the ammonia process, for instance. If there's any chemical engineers in the room, any chemical plant hates being turned down or ramped up. It's the riskiest part of operating a plant like that. So once again, trying to understand exactly what the flexibility is in your loads, really important when we go through these processes. And we're also in the process of trying to educate everyone on probabilities, because even if we think we know the resource, there's a chance that next year might be 20% less or 20% more. You know, and that's just the natural variability. That's not even taking into account the fact that we're still using satellite data, for instance, for solar resource, because they haven't got the measurement stations on the ground yet. So this is a slide, I've sort of thrown this together on some recent work. The top slide, so these are histograms of occurrence of a power generation point, okay? The top one's wind, bottom one's solar PV. You can see the bottom one there, solar PV, obviously nighttime, no production. Quite good actually at hitting its specified design point. So we get a little lump there. Wind is a little bit more dispersed through the whole distribution. The fact that you need a certain minimum wind speed means that you do actually get a lot of zeros in that production as well. And you also get a little bit of capping at the top end where you hit a maximum production despite more wind coming through. So if we take those same distributions and look at it on let's say we had a 50-50 mix of wind and PV in a certain project, you end up with a distribution like this. So you get a really lumpy production point somewhere in the mix of the capacity of it, so around 50%. You get a very long tail, so that So that installing transmission capacity, for instance, to export that tiny little bit at the end there becomes an economic decision. You know, is it worth for the 1% of extra production you get boosting up the transmission or the electrolyzers or all of the other little points down the stream? We also don't need 0 points because we can't shut down our facilities either. So shutting down the ammonia facility might take us 2 weeks to recover from. So that we've also got to avoid the bottom end as well. This is where something like CSP can come in to become very handy for us because we're actually able to schedule production out of the CSP facility, okay? And so we're able to capture all of those low points and basically load shift them up and produce a reliable source of energy for the essential loads. One of the things that we are discovering is that although ammonia is very inflexible, the electrolyzers do have a lot of flexibility in the way we can operate them. So that's where we tend to be able to introduce some of our flexibility. We can put hydrogen storage in there, and there's also points along the way that we can put energy storage as well. But also, as far as capacity factor of transmission lines or even electrolyzers go, if we can actually pull that distribution back, there are also some fairly significant project cost savings that we can develop in that space as well. So long duration energy storage is another topic that we're really just starting to get our heads around and look at the market of what the technology's out there. And there's actually a huge suite of technologies that are being developed, you know, gravity storage and all types of thermal batteries. So yeah, there's many different options being, and even pumped hydro can sit in that as well if the locations are right. Talking a little bit about our network design. So even if we can manage to get our production distribution tightly developed, LCOE no longer means LCOE for us because of the fact that we own the network. So a traditional LCOE stops at the gate where your facility is, and it joins a national network. The national network is stronger than anything within that gate. So you don't have to worry about voltage. You don't have to worry about frequency. A lot of those things that are someone else's problem. When we own the whole system all the way down to the port, suddenly all that becomes very relevant to us. And we actually have to come up with solutions. In a lot of ways, it's like a mini grid in that there's not a huge amount of generators, not a huge amount of loads, but it's a mini grid at gigawatt scale or hundreds of gigawatt scale. So we're trying to work out how we're actually going to manage these types of grids as well, because there's some really serious engineering challenges amongst there. This sort of summarizes some of those points. So we own and control all our generation, but also the loads. So when we start thinking about, is there flexibility in the loads, which in a normal network you probably don't have a lot of, we actually have complete control over the loads. So we can decide if things ramp up and ramp down. The optimization piece is really interesting. If you ask someone to design a piece of equipment, they tend to optimize it really well. But often a lot of the problems get shifted out into other systems. And even if you ask for the lowest LCOE system, often it's not the solution that actually fits the entire supply chain once again. So we're really trying to now approach our design as a complete system design rather than an individual component design. One of the issues this is unique worldwide. Something of this scale that we're trying to do doesn't really exist. There's no standards necessarily. We're working in all different jurisdictions around the world as well. So the actual rules change no matter what. Whether we interact with the national grid at all is a question that we're still trying to work out. A lot of the time we might look at PPAs to get things started before our own networks are operational, so that we need to meet standards that are happening on their own in those own projects. So that's our challenge. It's really taking those variable intermittent resources and delivering constant product output. So where's, I'm on my last slide. Good timing. So where's FFI going? So really there is demand out there for renewable green energy, but we need to make sure that we're actually securing our generation profiles to be able to deliver the products that we want to. Fortescue itself has a really good track record in innovating and coming up with solutions that that weren't apparent. I think the talk beforehand said that there's a certain amount of limitations in the existing grid as far as introducing renewables. We're actually designing from the ground up for renewables. So we're able to do things slightly different in that respect. 15 megatons per annum of renewable green energy by 2030 is challenging, but the ingredients are there, I think. So it's certainly a stretch target, but it's something that we truly believe that we can actually achieve. So I think it's going to be a very exciting next 8-9 years for me, especially. But you know, I think the goal's well and truly worth it. So it's going to be good fun. And that's it, right on time.
Okay, thank you very much. How exciting for you. So many things, so many opportunities. And just noting that one of the sessions this afternoon is on CST thermal storage. So we have a whole session on the different approaches, which might be interesting for you. Are there questions from the floor for Robbie? I can't.
Goodness, yes.
Okay, great. Thank you. Can you take
okay.
those, Renata?
Yes. First, I'm going to Alison Lennon. Sorry, just give me a minute. Leave your mask on, Alison.
Thanks, Robbie, for the really interesting talk, very inspiring talk. 15 megatons of hydrogen is a lot of infrastructure to be built, and that's going to require a lot of steel. Given Fortescue's investment in iron ore, could you elaborate a little bit more on the green steel question? Because look, to build all that PV or wind to power the electrolyzers is going to require a lot of steel. The electrolyzers are going to require a lot of steel. The green steel becomes a fundamental problem. And my understanding, the iron ore we have in Australia is largely hematite, and really to efficiently make green steel, we need magnetite. And so there is a process where you have to effectively upscale your hematite to magnetite. And so I was interested whether you can, or whether you're able to share with this audience Fortescue's plans in terms of green steel.
So it's a little bit out of my domain, I'll lead with, but there's certainly been a very concerted effort going on within the company looking at reduction of iron ores. They are using, I guess, the iron ores coming out of the Fortescue mines to do that. So they are addressing, I guess, some of the concerns you had there. The speed at which we can actually do that is going to be interesting for us to watch. There's actually so I sit within the engineering projects area. So we're looking at the really broad scale of how we actually achieve some of these goals. But there's also a manufacturing arm that are looking at how you actually build panels, how PVs, how we scale up some of the green iron technology. So there's actually a whole group dedicated to the manufacturing of components to make all of this happen. As I said, the company's very wedded to the idea that they own a lot of the supply chain that they need to achieve these goals. And then there's another group that's actually the technology group, which is really, I guess, where some of the more fundamental work sits as well. So there's a number of different, I guess, fronts there that are sort of all pushing at the same time. It's certainly challenging. There's no doubt about that. But I think one of the really nice things about what's going on there is they are prepared to invest and throw resources at a problem. There was a project recently that we had to put together very quickly, And you know, there was 50 or 60 people all gathered for a little 3-week sprint to put this whole thing together. And so that's the attitude within the business, that if there is a problem, you know, throw resources at it, and there is the capability to do that.
There's a question online here, which is related to what you've been talking about. You mentioned a 97% efficiency for green steel production. What were you referring to there, and what's that aspect?
We'd have to, as I said, that's outside my domain. And you'd have to refer back to some of the announcements that have come out of the company to look into the details of that at this stage.
Okay. Sure.
So I have Trevor Lee here now in the room with a question.
Oh, thank you. Robbie, I'm interested that the hydrogen industry generally quotes expected prices per kilogram, when the natural comparison, to my mind, is dollars per gigajoule, so that it's directly comparable with natural gas. I don't want you to do a quick computation on that just now, but can you give us an indication of the round trip efficiency if you're going to use the chemical energy in the hydrogen, and you start off with renewable electricity? What is the round trip efficiency in a targeted application?
I think we're still exploring that. It depends a lot on the final conversion technology. So if it's an ammonia engine in a ship, for instance, there's actually a number of inefficiencies along that way. If it's a fuel cell that needs a cracker to get the hydrogen back out of the ammonia, it's going to change again. So it's a little bit tricky to answer, but I think there's more to the answer as well. You know, it's not just a straight out efficiency. I mean, it's really around cost in the end, isn't it? And so to drive that cost down, sorry, we've really got to get our generation down. I mean, if we look at the cost of any of those products, whether it be hydrogen, gas, ammonia, etc., the biggest factor is actually the cost of energy that goes into the process. Electrolyzers, ammonia, and all of those other bits and pieces contribute, but the majority of the cost is actually in the cost of generation. So yeah, 30 cents per watt, I think, is Arena's target. Would be really nice, I think, if we could introduce those sort of numbers into our calculations.
Okay, are there any more questions from the floor?
I have one more from Anna Bruce.
Thanks, Robbie. Anna Bruce from UNSW. I was just interested to know, on the demand side for the green hydrogen, sort of how do you envisage that hydrogen being used in terms of what industries, and what kind of percentage of that demand would we meet with that 15 megatons?
I think the long-term vision is to basically replace oil and gas with some form of hydrogen-based fuel. So I think that's the end game. What percentage by 2030? I think it replaces something like a Mobil. So one of the big petrochemical companies that are basically the equivalent of their production.
Low-hanging fruit. Oh, sorry. What's the low-hanging fruit, do you think?
I think shipping's probably one of them, because you know, if we can get into the right ports, then that's one that I think we can have impact in. Wherever there's hydrogen pipelines already in existence, there's places in the US, for instance, that have already got hydrogen pipelines distributing hydrogen to all sorts of plants. So anywhere where there's existing infrastructure that actually can take the product and put it into use directly. As soon as we've got to ship at huge distances, then obviously that adds to the costs as well. Our own iron ore operations, another example where we can generate and actually utilize on the same site. So that's one of the key 2030 targets for us.
Okay, thank you. That's very interesting. And I think we're going to have to end the session there. Those of you who are live in Sydney can grab Robbie before he disappears and ask him more questions. But thank you very much for a very interesting presentation. We look forward to seeing what Fortescue Future Industries comes up with over the next few years.
Thanks very much.
Thank you.